So welcome to the last part of lecture 23 where we're working on our example. And just to kind of summarize what we've done before in the last part is we have this vector u1 which is our basis for the generalized eigenspace of 10. And then we saw these three vectors which is a basis for the generalized eigenspace of 20. And what we're going to claim is that this is the desired basis of the vector space V in order to get the correct shape. Okay, so first of all, you should notice that this is a basis of V. V was four-dimensional. And vectors from different eigenspaces are linearly independent, so there's no linear relationship between them. And in fact, you can go back all the way over to the beginning. Let me show it to you. Way back here. We said that our vector space V is this direct sum. So we found a basis for this part, and we now found a basis for this part. And since it's a direct sum, we can combine those bases together to get a basis for V. So that's what we've done here. We've kind of taken this picture, this statement here, and found a basis for each individual part. Now, for each individual part, we want to say something about it. Okay, so first of all, we want to claim that this is the desired basis that we want in order where the matrix in terms of the original theorem that we can get the proper shape. So what we want to do is take each of these basis elements and plug it into our function t. So when we plug u1 into our function t, we get the vector 10, 0, 0. Now, I should point out that I'm doing everything as column vectors, just to kind of save a little bit space here, and because I'm talking about matrices, right? So this is equal to 10 times the first basis element plus 0 times the second basis element plus 0 times the third basis element plus 0 times the fourth basis element, right? So I'm taking this element and writing it in terms of this basis. I can do the same thing for u2. When I plug u2 into my function t, I get this vector, and this is writing it in terms of my basis element gives me 0 times the first vector plus 20 times the second basis element plus 0 times the third basis element plus 0 times the fourth basis element. And oops, get rid of that. And now I've actually done the work here already for the other two basis elements. U3 gets sent to this vector, and here I've written it in terms of the basis is U1, U2, U3, U4, and I've taken U4 and I've written it in terms of the basis U1, U2, U3, U4. Okay, so we now actually have all the information, because if we use this as our basis, and we use our standard procedure of finding the matrix associated to it, well, we know, right, let's go back over here, U1 gets written in terms of this combination of the bases, right? So it looks like 10, 0, 0, 0, right? These are the coefficients, 10, 0, 0, 0. The next column is 0, 20, 0, 0, right? So 0, 20, 0, 0. What about the next columns? Well, the next column, let's see if I can get it on the screen here, is 0, minus 5, 20, and 0. And then the last column is 0, minus 10, minus 6, and 20. So there we are. We've now found a basis so that our matrix associated to this linear transformation is a block diagonal matrix where each of the blocks are upper triangular, and along each diagonal is the eigenvalue repeated to the multiplicity. Okay, and I just want to point out that you can actually see the original matrix here by combining a lot of these pieces of information. Notice that here these are the basis of C4 to find this matrix right here. So this is the block diagonal matrix, And this is the basis of C4 that we used to find it. This is the inverse of that matrix. And when you crank it out, I suggest that you go use a computer program. You're going to actually get back the original matrix way back at the beginning, the original matrix that we started with. Okay, so that's what will happen if you do that. Okay, what else can we say about this? So our original matrix actually wasn't diagonalizable, but in this case, we do get something that looks like a diagonalization result, right? Because our original matrix can be written as an invertible matrix times a matrix that kind of has kind of a diagonal type property. Okay, so I really hope that this example helps you kind of understand the key ideas that were being used in this theorem way back at the beginning. So when I presented it, it may seem very theoretical, but you can actually compute it. And this example here kind of shows you how would one go about doing that. So again, as I said, I hope this example kind of is very illustrative and you get something out of it. And going back now and looking at section 8.b, maybe a lot of this will help with this concrete example to play with. Okay, that's it for today, and I will see you in lecture 4 as we continue, lecture 24, excuse me, as we continue our discussion of chapter 8. Have a great day.